Thank you for the introduction. I'd like to thank the organizer for giving me the opportunity to speak here. So I will talk about Kähler-Einstein metrics on group compactifications and present the main result of my PhD thesis. So I'll try first. So recall what a Kähler-Einstein metric is and introduce group compactifications. So I'll deal with Kähler-Einstein metrics on a Fano manifold. So I'll take X a smooth, so compact complex manifold, but that will be Fano. So that's the still interesting case for Kähler-Einstein metrics, as Sébastien recalled yesterday, for Kähler-Viau or canonically polarized manifolds. There always is a Kähler-Einstein metric. So in this case, I'll define rather what it means for X to be Kähler-Einstein. So that means there exists a Kähler-Einstein metric, but I give another, well, slightly different definition. So X is Kähler-Einstein, and I'll say Ke if and only if there exists a Kähler form in 2 pi times the first Schoen class of X. So Kähler form which satisfies the Kähler-Einstein equation, which is Ricci of omega is equal to omega. Ricci of omega is the Ricci form of omega. This is a 2 form that also lives in this class. And it encodes the Ricci curvature of the Kähler metrics, the Riemannian metric associated to the Kähler form. So as I will use it, I will recall the local expression of Ricci of omega, which can also serve as a definition. So in local coordinates, so we can write omega as IDD bar phi. Phi is a local potential of omega, and then the Ricci curvature has the following DD bar potential. So the DD bar potential is minus the log of the Monge-Ampère operator of phi, that is the determinant of the complexation. So that's why Kähler-Einstein metrics are related to complex Monge-Ampère equation, the original definition of Monge-Ampère equation. So the main results in recent year about Kähler-Einstein metrics on Fano manifolds is the resolution of the Yao-Qian-Donaldson conjecture by Chen-Donaldson-Sun or Qian. And that says that X is Kähler-Einstein if and only if X is K-stable. And recently, Data and Zekeleidi obtained a stronger version. So, in particular, in the case, well, this is different in the case where X admits a group action. Then it is Kähler-Einstein if and only if it is equivalently K-stable. So I will not go into the details because I don't use K-stability, but this is a way to take into account the G action and maybe this could be used to recover my result, but at the time I did my work, there only was this result, and case stability, the original definition, cannot be checked on examples. There's an infinitely many test configurations that you don't know in general for manifolds and for Fano manifolds, and infinitely many ways to degenerate to these manifolds, or varieties. And you cannot compute the Nelson-Futaki invariance. So there are no examples known before that are exactly these results of proving that a manifold is Kähler-Einstein using case stability.
In this equivalent context, the metric is G invariant?
Yes, so G if G is compact. Okay. Yes, but I will recall this later. So I'm really considering examples of Fano manifolds and trying to give a criterion for existence of Kähler-Einstein metrics using this extra information. So an example of such a result, a really important family of Fano manifolds is for toric Fano manifolds. So it's a theorem obtained by Wang and Zhu in 2004. So if X is a toric manifold, Fano manifold, so it is Kähler-Einstein if and only if the barycentre of the associated polytope is the origin. Oh. And my goal is to present a similar result for group compactifications. So I'll introduce now group compactifications. So let G be a complex connected reductive group. For example, GLNC, then X. So I still assume for the talk that X is smooth in Fano, is a compactification of G. So if I have an action not only of G but of G times G on X, with an open dense orbit, which is isomorphic to G as a G times G homogeneous space. So here on G, the two actions are multiplication on the left and on the right. So I'll first give some examples and then define an associated polytope, just as in toric manifolds. So the first example, or series of examples, are toric manifolds. So this is a natural generalization of toric manifolds. So this is in the case where G is G complex torus. So in that case, both actions are equivalent. It's the same as taking only one action. And so these are not the only examples, otherwise I wouldn't add anything. But there are examples, let's say for any type. So these are the wonderful compactifications of adjoint summit sample groups. So they were constructed by De Concini and Procesi. So if G is an adjoint semi-simple group, then there exists a compactification of G in the sense that I wrote here, so it is smooth and Fano. And so why is it wonderful? Because it satisfies some nice properties. So I just recall them. So the boundary of G of X is a union of simple normal crossing divisors. And all orbits, well, if you take any subset of I, all intersection of subset of divisor is the closure of a unique G times G orbit. And all orbits appear in that way. So I will now describe the associated polytope, or rather polytopes. There are many polytopes associated to group compactifications. I give only two. So before that, let me introduce some notations and choices. I'll choose T and G a maximal torus. And let M be the group of characters of T. Let phi denote the root system. Of G with respect to this torus, and choose positive roots. And let also W denote the Wide group. So the two polytopes associated to X will be given by the following theorem, that is a consequence of general results by Briand. So there exists a unique lattice polytope in M tensor with R. So lattice means its vertices are in M, are characters. W invariant, and which gives the decomposition of the space of sections of the anticanonical line bundle as a G times G representation. So all the irreducible G times G representations that appear are of these forms, where V lambda is a G representation of highest weight lambda, so irreducible representation, and the weights that appear are given by the lattice points of P, but that can be highest weights, so that are dominant. And then I defined another polytope that is the intersection of P with the positive Weichamber. So whose lattice points are exactly the weights that appear here, but it doesn't have necessarily, it's not a lattice polytope in general. So with these definitions, I can give my main result. So a compactification of G it is Kähler-Einstein if and only if. So there is a condition involving a barycenter of P plus. And another part here. So 2 rho here is the sum of positive roots. It's a usual notation. Sigma is the relative interior of the cone generated by the positive roots. And the barycenter is a barycenter of P plus, but with respect to a special measure. So let me write the expression. So we integrate P, a point of the polytope with respect to the measure. So this is the Lebesgue measure normalized by the lattice, and the weight in front of this is product of the positive roots applied at P and squared. So over the same thing, but without the P here, of course. So the situation is that you have the positive Weichamber, and so the polytope P plus is the intersection of a W invariant polytope with the positive Weichamber. This is P plus. The point 2 rho is always in the polytope P plus. And then you're looking at the relative interior of, in this case, the dual cone of the positive Weichamber, but translated by 2 rho, and the barycenter have to lie in this zone. Okay, so this is a criterion that is computable. We can check if we can compute the barycenter with this, with respect to this measure of a polytope. And so this gives examples, new examples of Kähler-Einstein metrics, but also examples that do not satisfy this criterion. So examples. So all so my examples will only be in small ranks because the computations are easier. All wonderful compactifications in rank 2 are Kähler-Einstein. And there exists a compactification of the symplectic group, complex symplectic group of order 4 that is not Kähler-Einstein, with, in addition, this example as vanishing Futaki invariant. And is not K-semi-stable. So I will not explain these two things, but there were examples, of course, with 2 of these things, but with the 3 at the same time, I think not. Okay, so for the rest of the talk, I want to explain how we can use the special structure of these manifolds to translate the Kähler-Einstein equation into a real Monge-Ampère equation, and how we can use this and how the condition appears. What compactification? Yes, so it's rank 2. Yeah. It's invariant under, so this is the starting point. Maybe I'll just give this here. So it's not G invariant, but the starting point of the thing. Why do we consider manifolds with symmetries? It's that it's part of a result of Matsushima. So if omega is a Kähler-Einstein form, then the group of holomorphic isometries of omega is a maximal compact subgroup of the group of automorphisms the connected component of identity in the group of automorphisms of X. In particular here, the consequence is that we can assume that omega is K times K invariant, where K is a maximal compact subgroup of G. So it's not G invariant, but K times K invariant. Okay. So how are we going to use this? First of all, so we have this K times K action that will simplify things, but also we have a privileged open subset of X, that is the group itself, the open orbit. So we get this big orbit G, and then I would like to use the K times K action. So if I have a description of the K times K orbits, that will help. So to describe this, this is known thanks to the K decomposition of a reductive group. So to describe this, I will use the following subset of the Lie algebra of G, or sub-Lie algebra. It's a Cartan sub-Lie algebra, but I write it explicitly. I take the intersection of the Lie algebra of T and I times the Lie algebra of K, so it lies in the Lie algebra of G and is sent in G by the exponential. It has an induced, well, it has an action of the Wald group. And in fact, the two things correspond, and the quotient for this action are both isomorphic to, I'll denote that A plus bar, that is the closed positive Wald chamber in A. You can naturally see it in A. So how are we going to use this? So we have to start from a Kähler form in the given class. That is K times K invariant. On G, this will have a global potential, dd bar potential, phi, that I can assume K times K invariant. I can always find some K times K invariant dd bar potential for a K times K invariant form on G. And then I will go from there to there by taking the function phi composed with x, so function from A with real values. And the K times K invariant here, function here, corresponds to a W invariant function on A. So this is the first step, but also phi as a dd bar potential of a Kähler form is PSH. So that corresponds to, so strictly PSH and smooth, that corresponds to U being smooth and strictly convex. This is the theorem of Azad and Loeb from 92. So we can associate to omega a strictly convex function on A that determines omega. And in addition, so this was just a correspondence between K times K invariant function on G and W invariant function on A, but we took them coming from a Kähler form in a given class. So that means that we can assume, we can choose phi and the corresponding U, so that we have U minus V is bounded, where V is a support function of the polytope, or rather 2 times the polytope P. So the formula is the following. So just as a remark, this is kind of related to what Sebastian told us about during his lectures. So here, if you take only so G over K is the symmetric space, that he looked at, and A is a flat in G over K. And if you quotient in addition by K, you have not only, well, if you look only at a flat, you have always one element of the K times K orbit, but you have also this W action induced, and in fact this is a fundamental domain, is a Wald chamber. So that is the first thing. And also, it will only be really formally, but this function here, you don't have to consider all the points of the polytope, but only the vertices. And formally, this looks like the non-Archimedean function associated to the, so here's the metric omega. But this is just formally. Okay. So now I want to use this to translate the Kähler-Einstein equation in terms of this function, this convex function u. So I start from recalling, so the Kähler-Einstein equation is this. I can restrict this to the open orbit G. So this part here is IDD bar phi. And here, if I choose local coordinates near every point, I can use this expression that I recalled last time, well, earlier. And in well-chosen coordinates, I can even get rid of the IDD bar. This part here will easily be translated into the u function, but here there's some work. We can compute this for a k times k invariant function, the complex Monge-Ampère of phi, at a point in the image by exponential of the, well, point in the open Weis-chamber, positive Weis-chamber. This is a computation that I did to express this in terms of u. And this will brings in the real Monge-Ampère of u, the determinant of the real Hessian, and then a term, a gradient term, determine the gradient of u, and also another term that depends only on the position. So using this, we can translate everything in terms of u, and let me write what this becomes as a real Monge-Ampère equation. So if I rewrite this a little bit, so this is this operator equal to E minus U. This is the term coming from here, and I forgot this part that I add here. I write this as E minus U plus J, whereas J is minus. So this is the first part, the translation into a real Monge-Ampère equation. So here, now we are only dealing with convex functions in real Monge-Ampère equation. Tool in this setting is the convex duality. So finite dimensional here, but so the idea is that the idea is to use, or in this really smooth and finite dimensional case, it's to use a change of variables so use as a new variable the gradient of u at x. And so I won't use this on the full, so on the equation directly, because it works well with this part, but with this part it works less well. So I will rather use this on some integrals. First, to give an example, but that will be useful. If I look just at the integral of the operator here, well, applied to u, of course. So if I look at the integral over a plus, the positive Weichamp of this term, and I use the change of variables, this will transform this whole thing here into just dp. Here the gradient is replaced by p. And we need to know what the image of a plus is by this variable change. But this is just 2p plus. So this is saying that exactly what I said. The image by the gradient of u of a plus is 2p plus. This is implied by what I said earlier, that u minus v is bounded, and also that u is convex, of course. So this is exactly what appears here. And what is the above part? This is just, so if I look at the integral of the gradient of u and this measure, this will give the above part. So this is also, let me give this, denote this by v, and this is the barycentre of 2p plus here times v. Just to make the barycentre appear. For now it's unrelated to any equation. But okay, let me use another notation. So this thing that I keep writing. I define nu as the minus the log of this thing here and the Kähler-Einstein equation. Then it's just that nu is equal to u plus j. Look at this equation here. So if I start from this, so if I assume that there is a solution, I can consider this. Take the derivative in any direction. This is still equal. Then I multiply by something that is non-negative. This is still, of course, equal. And then I integrate this over a plus. This is still equal, of course, but so this seems really stupid for now, but this quantity here vanishes for simple reasons. So it's just applying some Stokes formula and using the fact that e to the minus mu as an exponential decrease. You can show that rather easily. So this is equal to 0. And here, if I cut it in two, I will have, so I have 0, which is equal to, let's just rewrite this. This part here is just this integral here, but taking the scalar product with psi. That's what I mean, in fact, by the derivative in the direction psi. It's that it's the gradient of u scalar psi. So this gives me, this first term gives me the barycentre of 2p plus times v scalar xi. And I still have this other integral. But this is an explicit function, and I can show that if xi is a direction in A plus, I always have that this derivative at any point is smaller, strictly smaller than minus 4 rho psi. Okay, sorry if it, I rewrite the consequence here. So that means that 0 is strictly smaller I take this, I use this inequality here and derive that this is true for psi in A plus, and I divide by v, of course. So I have this inequality for psi in A plus, and that exactly means that this is in sigma. So this is exactly my condition here. Well, divided by 2. So that shows that my condition is necessary and how it appears. So seems a little strange, but in fact it is rather similar to the original reason why the Futaki invariant is the vanishing of the Futaki invariant is a necessary condition for having a Kähler-Einstein metric. And now for the sufficient condition, that's harder, but that's where I got the condition, in fact. So we use the continuity method. So here that will translate as the equation. So nu t will be this thing here with ut. So ut is my new unknown function. Plus j. So I modified the equation there. I've considered a family of equations. For t in 0, 1. So that corresponds, I should have said that first, that corresponds to not the Kähler-Einstein equation, but something close. So that corresponds to this equation, where this is a fixed Kähler form in 2 pi c1 of x. It's translated by the same proof as this equation. And so the continuity method, this is trying to prove, so at t equals 1, this is the Kähler-Einstein equation, and at t equals 0, this is equivalent to some Calabi-Yau theorem. Well, in a special case, of course. So this is part of classical results. So if I consider the set of T such that this equation there is a solution, I want to show that one is in I, and the classical results due to Aubin and Yao are that I is non-empty and open, and it is closed if and only if we have some estimates, some a priori estimates on the solution, which in our setting translates as this condition. So in case it is closed, of course, one is in this set because it is a connected subset of I, of 0, 1. And so the thing we need to check is that there is this kind of estimates. But we can show without any condition on X, well, a compactification of group compactification, we can show that these estimates are a consequence of another estimate. Okay, so I'll just write it. So what is xt here? Where xt is the point in A plus where nu t has its minimum. So we can also show this, that nu t has a unique minimum, which is strictly convex and proper in some sense. So we can show this without any condition on the polytope. And then, so we assume now that there are no Kähler-Einstein metrics. Then we can assume, up to taking a subsequence, that this quantity goes to infinity as t goes to some value t infinity. And at the same time, we can also assume that the direction psi t has a limit, still up to taking a subsequence. And then we'll use the same kind of formula as here, but with nu c. So my equation is this. I can still use this this type of thing. So this is equal to 0 for the same reasons. And so I got this thing here. And then, so of course, the ut part will still give me the barycenter. But for the other parts, I have to use a limit argument. So that gives me the barycenter. Apply that limit psi infinity. And there are other terms, of course, so this is times t infinity. And these other terms are 1 minus t infinity times the support function applied at t infinity, and minus 4 rho at t infinity. So I don't know how much time I have left. No time, so that's okay. I mean, that's what I wanted to say. Yeah, okay. So to show that these other terms converge to this is the main technical part of the work, but it works. And this part is, was already kind of expected in the toric case, and this is really the hardest part. The thing is that you ref as the asymptotic behavior as the same as V, and J has the same asymptotic behavior as -4 rho, but only outside of the walls of the chamber. But I cannot go into the details here. Thank you.